All right, well, we are going to continue our discussion of capacitors, as you can probably tell. Sorry, I just want to make sure everything's recording. So more fun stuff on the way as it relates to capacitors. But first, we should review the previous lecture, in which we introduced the idea of capacitors. And so the basic prototype for a capacitor is two pieces of metal that have some charge on it. And there's two different sort of ways to use capacitors. One is you can connect them to a battery, as in this diagram, and in this. So when you do that, the positive end of the battery sucks in as many of the electrons as it can, and it shoves as many electrons as it can, so that one plate is positive, the other plate is negative. And when I say as much as it can, what I really mean is that this battery is very good at maintaining a particular potential difference between the two leads. And so it will suck in electrons and shove electrons until the point where the potential difference across these two pieces of metal is the same as the potential difference across the battery. And maybe the battery is 12 volts, maybe it's 5 volts, maybe it's 1.5 volts. A lot of, AA, AAA batteries are 1.5 volts. But anyway, it's going to do that until that voltage is achieved. And so that's one way of that's one way of using capacitors, and there's types of problems that look like this. Then the other type would be when you charge up the capacitor like this, but then you disconnect the battery, and now you've got a bunch of negative charges on this plate, and sort of this plate is missing a bunch of electrons, so it's overall positively charged. And there's a class of problems you can do with that of, what happens when you discharge the plates and you connect a wire from one side to the other, or you make sparks, something like that. So these are the two kind of types of problems that you might run into. We discussed that the larger the potential difference, so this battery has some voltage attached to it, but the more voltage of the battery, the more charge will build up on the plates. So there's a demo I like to do where we actually have this device that can control the voltage. So it's not a battery. Instead, you have a knob that can tune the voltage from 0.1 volts all the way up to, I think, 20 volts or 25 volts. I can't remember. And so the more volts that you have, the more charge that you get. And indeed, if you take a capacitor, connect it, and then you disconnect it from the battery, put a paper clip across it to make it spark, the more voltage you put on the capacitor, the bigger the spark, which tells you that the more charge has been stored on those plates before you disconnected it. So there's a proportionality here. The capacitance is just a proportionality constant. So as long as you're not changing the size or shape or material that the capacitor is made out of, and typically you're not, the capacitance will be the same. So this is a useful equation. Every semester I've taught this course, students have sort of accidentally used some other version of this. But here it is. This will be on your equation sheet in any case. The new unit is called a farad after an English physicist named Michael Faraday. And the important thing is that more capacitance, so if you have some voltage here, more capacitance means more charge. So if you're thinking of designing a capacitor bank to make some new electric car go faster, like Porsche has an electric car now, you want the capacitance to be large so that you can store as much charge on those capacitors, so that when you need that extra kick, it's there. So we showed that this is the equation for the capacitance for two charged plates. There's various other equations for things that are not two charged plates, but this is what we found for the two charged plates. So the capacitance can change if you are changing the separation between the plates, or I don't know how you would increase the area of the plates, but in principle the capacitance can change. But typically you're not changing the size of the plates. You're not, when we're using capacitors in a circuit, we're typically not messing with it like that. So typically this is just a constant. And this, by the way, is the dielectric permittivity of free space. All right. We talked about how if you have a circuit, and the capacitors are wired up like so, that you can think of these capacitors as being sort of like one capacitor with this capacitance. And we talked about how you derive this equation, where it comes from. We talked about how if you have a circuit that looks more like this, that if you had one capacitor that does the same thing as these two capacitors, that equivalent capacitance would just be the capacitances added together. Okay, so something I wanted to talk about last lecture but I didn't get a chance to was this situation. So what I'm saying is that if you look closely at the slides for last lecture, you'll see this sort of a thing discussed, even though the video wasn't really unpacked. And so I want to talk about it now. And the question is, what does the potential look like with distance for the situation? We have a battery. It's connected to two sort of sheets of metal here. So again, it's causing this plate to be positive, this plate to be negative. What does the electric potential with distance look like in this case? Well, if you think of the electric potential as being the potential energy of a positive charge, if you were to put a proton over here next to this plate, the potential energy would be very large because I could let go of it and that proton would be able to accelerate this way and get up to a nice high kinetic energy. But if I put the proton over here next to the negative plate, it's only going to be able to accelerate by for a short amount of time before it reaches this negative plate. And so the potential energy over here is not so much. So high potential, low potential, you end up with something like this. And a lecture or two back we had a long discussion about how the electric potential in a situation with a uniform field goes as minus ED, where D is the distance along the field lines. So this is something we've discussed before. What we've not discussed before is what happens when you have these two charged plates and you put a piece of metal in between the two ends. What happens now? And so, so let me unpack that. So part of the answer to this question is that whether this thing is charged up or not, in this case it's actually not charged up, but whether it's charged up or not, inside of a conductor, such as this metal plate, the electric field is always zero, and the electric field is related to, the electric field equals minus the derivative of the voltage versus distance. And so if the electric field is zero, that means that the voltage has to be constant. And so the one thing we know is that inside of this thing, the voltage needs to be constant. Now out here, in between these two plates, the voltage does not need to be constant, because it's not inside of the conductor. Same thing over here. The voltage out here does not need to be constant, but at least inside of this conductor, it needs to be constant. So at the end of the day, you would end up finding something like this would be the result of, again, taking basically this capacitor and putting a piece of metal in it. So again, it's flat because the electric field is zero. So if you think carefully about this and you compare it to the case where this piece of metal is not inside of there, you will find that before it was doing this, and so now it's kind of like the potential is changing more rapidly with distance. Remember that delta V is equals to minus ED. Well, the only way this can make sense is if the electric field is larger than before, right? Because the distance traveled from here is the same as it was. So the electric field is larger than before, and so not only is there charge building up on here, but putting this inside of here, because the battery is forcing the potential difference from here to here to be the same thing, at the end of the day, putting this piece of metal in causes all these charges to increase. And again, they increase because you have to have a larger electric field to make this potential difference the same as the battery. And the only way to do that is to increase the charge on the thing. So again, as soon as you put this piece of metal inside, you actually find that more electrons are finding their way into the battery and more electrons are getting shoved onto this end, which is interesting. So again, if you take a capacitor and you shove something inside of it like this, you end up increasing the charge on the capacitor. Now, what happens if you have a piece of plastic? Let's say if it's a piece of plastic instead of a conductor. Well, in a plastic, the charges are not 100% free to move, which means that the electric field does not necessarily need to be zero. And so you don't expect it to be perfectly flat in the middle. But because the charges have some ability to move from one side of the atom to the other, even though that's not very far, that does change the electric field somewhat. So instead of having something like this, you're going to end up with something like this, where the electric field is sort of weaker than it, well, the electric field is larger than it would be if there was a piece of metal here, but it's not totally zero. And so at the end of the day, you're still getting an electric field over here, an electric field over here that's larger than it was if you had nothing inside of here. But anyway, this is the effect of putting some sort of piece of plastic. A dielectric is a very fancy word for a piece of plastic for the most part. So let's think about this again. So we have the two plates, and we put a dielectric in there, or a piece of metal in there, and we found that even though the potential was the same, we found there was more charge onto there. So again, it was connected to the battery, so the potential difference was the same. The charge increased. So the only way that that makes sense is if the thing that we did to the capacitor actually increased the capacitance, whether we're putting a piece of metal in there, putting a dielectric in there. It seems like in that situation both those situations, we ended up increasing the capacitance effectively, because we certainly didn't change the voltage. We didn't change the battery, we didn't up the voltage on the battery, which is not really possible. Again, shoving something inside of the capacitor increased the capacitance. I think I already said that, don't do that. Now let's say that, now let's think about the situation that instead of having the battery attached, let's say the battery isn't attached, and let's think about it that way. So I think that's what we're going to do in the next part. So again, in this situation now, this is not a battery, this is a multimeter, and it's telling us what the voltage is across these plates. And it turns out that if you put a dielectric, which again is a fancy word for a piece of plastic, in between these two plates, if it's charged up, like we already charged it up with the battery, now we're just measuring it with the multimeter. If it's charged up and you put a dielectric in here, this actually decreases the voltage that you would measure across. So if you look carefully at this thing, it says 2 volts, no dielectric, 1 volt with dielectric. And so just schematically here, if we got rid of this battery, here's what would happen. We put a piece of metal in here. Now it is no longer the case that the potential difference across these things has to be equal to the potential of the battery, because there's no battery. The charge is stuck on here as the charge is stuck on here. So that's not going to change. We're not going to increase the charges on here. But because there's a piece of metal here, the electric field in the middle here is going to be 0. And because the charge isn't going to change, we're not changing the electric fields necessarily, but what is changing is the potential difference across these two things. Okay? And so if you think about that in terms of this equation, the charge is fixed now. It stays because the charge is trapped on those plates, like when I like to do that spark demo. But the voltage has actually decreased. The change in the voltage difference across those plates have decreased. So the only way that this makes sense is if the capacitance has increased. Again, the capacitance increased because we shoved something in between those two plates. And so again, it's helpful to put dielectrics between those two plates. Now, I've talked a lot about putting metals in between the plate, right? I've talked a fair amount about that, and as you can probably see, that if your goal is to increase the electric field between those two plates, putting a metal actually works somewhat better than putting a dielectric. But here's the problem: is that if you put metal all the way from this plate to that plate, what happens to your capacitor system? Well, if you have a conducting path from this plate to this plate, it's just going to conduct all that charge. So you really want some sort of insulator inside of here if you're going to try to make the electric field stronger than it was. So even though it's not going to be as effective as having a piece of metal, at least it's not a conductor, because that would be bad. The last thing you want is like sparks or charge jumping across. You want to be able to charge this thing up, hold on to that charge, disconnect the battery, and then use that charge when you need it. You don't want to like accidentally discharge because there's metal in between those two plates, or like you bump it, you like bump the thing and it accidentally goes off or something. All right. So I think I said all these things. All right. So With dielectrics, again, dielectrics are a special kind of insulator. Um, there's a nice table in the book. So it's table 25.1. Your table probably looks a bit different. This is from the previous edition of the book, but these are all examples of dielectrics. Now, technically, not all these are plastics, right? So some of them are. So polyvinyl chloride, does that sound familiar? PVC, you know what I'm talking about? That's plastic. Polystyrene is, most plastics are made out of some form of polystyrene. So, you know, maybe dielectrics are not always plastics, but it's pretty often they are. The main thing to notice is that there are no metals on this chart. There's no aluminum, there's no copper, there's no gold, there's no silver. It's all things that are insulators. And this table lists what's called the dielectric constant, and this is a constant that goes into calculating the capacitance. The important thing is that if you don't have anything in between those two plates, so for example, vacuum down here has a dielectric constant of 1.0, that's because it's not actually increasing the capacitance. Putting vacuum in between the plates, there was already sort of vacuum in the plates. Anyway, the vacuum does not increase the capacitance. But putting anything else in between those two plates increases it substantially. Strontium titanate, which I actually think is part of the Apple pencils. I have to check that out. That's interesting. But these all increase the capacitance that's there. And so this dielectric constant, this symbol is actually not K. It's technically, we would call it kappa, which is the Greek letter. So if you want to know how the capacitance changes because you put material in there, this is the equation to do that. Now the other part of this table, that's right. The other part of this table is the dielectric strength. And one entry in here should be somewhat familiar. So if you remember from earlier in the course, I told you to assume that assume that sparks would happen if the electric field exceeded 10 to the 6 newtons per coulomb, or 10 to the 6 volts per meter. Here it says that dry air will spark if the dielectric strength is basically the electric field for which sparks occur. Like if this electric field's above that, a spark will occur. And so this says 3 times 10 to the 6. So maybe I was lying to you a little bit earlier. Maybe the electric field needs to be closer to 3 times 10 to the 6 instead of 10 to the 6. I don't feel so bad. But in any case, this is where that comes from. And so what's interesting is that if your goal is to put as much charge on this capacitor bank as you can, so that you can use it in some fun application like making a Porsche go faster, there's lots of things that have a higher dielectric strength than air. So, and maybe you even want to suck out the air. So in one of the earlier worksheets, I think from last week, I talked about how if you have this hospital machine and there's a potential to make sparks there, and maybe you should suck out the air. Well, vacuum here has no dielectric strength. You can have arbitrarily high electric fields, and if there is no matter from one positive end to the negative end, then there's nothing that can make a spark like that, which I think is pretty interesting. So that's an interesting part for this table. I think I said most of these things already. So I tend to think of it as like a breakdown strength, a dielectric strength. So that, by the way, there is going to be at least one question on the midterm, basically saying, all right, we're trying to put as much charge in this thing. Let's replace the air with this material and this thing, and how much more charge is it? Is it going to exceed the dielectric? Is it going to break down, or is it going to be safe? So that's a good question for the midterm. Now, what exactly is happening on a microscopic level that allows this all to work? Like when you're using a dielectric, and why does it only partially shield the electric field? So this is an insulator, and the important thing of this animation is that the charges can go from one side of the atom, so like this one goes to that side of the atom, and goes back to this side of the thing, but the charge does not go all the way over here, for example. So on the microscopic level, this is what the electrons are doing. And what's interesting about that is that when you put something like this in an electric field, so it turns out that molecules tend to have positive end and negative ends. If you add them together, they're neutral, but they tend to have like H2O has a positive end by the hydrogen and the negative end by the oxygen. Pretty much all, many if not most molecules do that. And so what happens is that if you have a substance like this and you put it into an electric field, it tends to align the things so that you end up with sort of a positive thing over here and a negative thing over here. And at the end of the day, if nothing was in between your plates, it would look like this. But if you put a dielectric in it, you end up with positive stuff over here, negative stuff over here. That at the end of the day, that makes the electric field a little bit less. Do you see how cleverly I changed the line shape of the electric field? Again, the result of the dielectric is to make this electric field somewhat less. That's what's happening microscopically. So if we are trying to figure out how much charge we can store in this thing, I just want to talk about an equation from the book, which I think is on the homework. It's not going to be a big deal for the midterms, but I feel like I need to talk about it, which is that the equation for how much energy is stored on a capacitor is Q squared over 2C. Remember that Q equals C delta V, so I can take one of those Q's. Q equals C delta V, so if I put that in, I get this. And then I can take one of those C delta V's and make it into that. So these are all equivalent. The moral of the story here is that if you have some particular voltage source that you have, say you're connecting it to the car's battery, which is 20 volts or something like that, the more capacitance, the more energy that it stores. And so if you can use a dielectric to double the capacitance, then potentially you can double the amount of energy that is stored in that thing. And so if you can do that, then your boss will be very happy, right? You've managed to double the usefulness of this capacitor thing. So again, the energy capacitor is not so important to us now with midterm 1, but it'll come up in midterm 2. By the way, this should be 25.4, I think. So I think I said all these things. All right, so that's about it for today. We're going to do another worksheet today on capacitors, and so get ready for that.